Hello friends. So today we are going to solve the questions, and these questions are from the year 1997 and 1998. From the year 1997 we have 4 questions, and from 1998 we have 6 questions. So total we are going to solve 10 questions. So in the first question, which was asked in the year 1997, and it states that an eye specialist prescribes spectacles having combination of convex lens of focal length 40 cm in contact with concave lens of focal length 25 cm. The power of this lens combination in diopter is. So this is quite straightforward, based direct on the formula, and we can say that power of the lens combination, power of lens combination, if that is represented as P, then P will be equal to power of first lens plus power of second lens. And we know the relationship between power and the focal length. So power will be equal to 1 upon focal length of first plus 1 upon focal length of second. And the focal length is given in centimeters, 40 centimeter, 25 centimeters. So therefore we can write this as 1 upon 40 plus 100 upon minus 25. Because for concave the focal length is taken as negative and convex for focal length is positive. So this will be giving us 2.5 minus 4. So we get that the power will be equal to minus 1.5 diopters. So the option number B is correct. Option B is correct. We come to the next question, and here it was also asked in the year 1997, and it states that in Young's experiment the upper slit is covered by a thin glass plate of refractive index 1.4, while the lower slit is covered by another glass plate having the same thickness as the first one but having a refractive index of 1.7. Interference pattern is observed using a light of wavelength 5400 angstrom. It is found that point P on the screen, where the central maxima fall before the glass plates were inserted, now has 3/4 of the original intensity. It is further observed that what used to be fifth maximum earlier lies below the point P, while the sixth minima lie above point P. Calculate the thickness of the glass plate. Absorption of light by the glass plate may be neglected. So in this case, we have a, you can say, Young's double slit experiment. In that case, there are 2 slits. One slit is covered by the refractive index 1.4 and another one is covered by the same thickness but refractive index is 1.7. Okay. So in this case, it was found that a P on the screen. Okay. So after this insertion is made of the upper, rather you can say their slits are covered with the refractive index of 1.4 and 1.7, it was observed that now only the 3/4 of the original intensity was observed by the at the central maxima, that is at point P. And there is also a switching of you can see fifth and sixth minima above and below. So we have to find out the thickness of the plate. Okay. So this entire discussion can be divided into two parts. In first part, we can say that both the slits are having same thickness, the refractive index is 1.4, and it means they will be traveling the same path, so there will be no path difference, and the central maxima will be at point P. Later on, one of the slit is replaced by higher refractive index, that point 1.7 suppose, and because of that the higher refractive index leads to, you can say, path difference between the two beams. So likely there will be shift in the interference pattern, and because of this shift in interference pattern, the intensity at point P will be also reduced, as mentioned in the, that it's the 3/4 now. Okay. So let us start with the initial two parts. So you can say that initially and both slits have identical glass plates and which means same thickness and refractive index is 1.4 and refractive index is 1.4. So from here we can draw in conclusion that a light from both the slits travels through the same optical path. Light from both slits travel through same optical path. Through same optical path. That is, there will be no path difference. No path difference, and central maxima is at point P. And central maxima is at point P. So this is initial condition. Now we come to the, you can say, final condition. And final, it says that one glass plate is replaced by another glass plate with the same thickness but higher refractive index, that is 1.7. So you can say from here that replacement of glass plate same thickness but higher refractive index. Higher refractive index, and that is our 1.7. Therefore, we can say that, and let us suppose this we do in the upper slit. So the change is made of the sheet is in upper slit. So we can say that there will be the path difference between the two beams. Path difference between the two beams, and as the path difference, this also results in the phase difference. And because of the phase difference, there will be two important effects. First is that shift in the interference pattern, shift in the interface pattern, and secondly, there will be a reduction in the intensity at P. Reduces intensity at P. So let us, and because of this delay, the central maxima is going to move. So we can say that due to delay, central maxima moves. Central maxima to move, and secondly, we can also say that now the point P has partial destructive interference. Okay. Point P has partial destructive interference. Destructive interference. So its intensity drops. And which is also mentioned in the question, that it states that the fifth maxima appears below P and there is a sixth minima appears above P. Sixth minima appears above P. So let us solve it now. So we are going to first of all find out what will be the path difference introduced by the glass plates. Path difference due to glass plates, and we have two refractive indexes. Let us suppose we have mu1, which is our 1.4, and we have mu2, that is our 1.7. So we know the formula for the path difference, that is our delta is equal to mu2 minus mu1, and this is multiplied by T, where this T is the thickness, which is same for both the plates. So we substitute we get this as 1.7 minus 1.4 multiplied by t, and this comes as 0.3 t. And the phase difference and intensity at point P. Phase difference and intensity at P. So initially there was zero path difference and having the equal amplitude. So we can say initially there was zero path difference and they were having equal amplitude A. Equal amplitude, let us suppose that is our A. So therefore we can say intensity at P that is our I naught will be equal to A plus A, and this is whole square giving us 4A square, and this was initially, and finally means adding glass plate, phase difference is introduced. Let us suppose that is our delta. Phase difference delta is introduced. So we can say new intensity let us suppose that is given as I will be equal to A square plus A square plus 2A square cos of delta, and we can write this as our I will be equal to, we can take 2A square as common, this plus and cos of delta, and it's also given that the intensity becomes 3/4. Okay. So we can write that 3/4 of I naught is equal to our 3A square, and this is given to us in the question. So we can equate, and we can write it as 2A square, and we have this as 1 plus cos of delta is equal to 3A square. Yeah, 1 second. Let me solve it. It looks, this is 3/4 of I naught, and I naught is our 4A square. So this comes as 3 upon 4 multiplied by 4A square. This 4 and 4 cancels out, and this is equal to our 3A square. So new intensity is our, if we equate them, and from here we get 1 plus cos of delta is equal to 3/2, and you can write that our cos of delta will be equal to 1 by 2. Cos of delta will be equal to 1 by 2. So therefore we get that our delta will be equal to pi by 3, 5 pi by 3 and so on. So let us taking the smallest positive phase shift. So we can say considering smallest positive phase shift, that is delta is equal to pi by 3. And now we can create an equivalence between the path difference to phase difference. You can say connecting phase difference to path difference. So a path difference is our lambda upon 2 pi multiplied by delta. So this gives us 0.3t will be equal to lambda upon 2 pi and multiply by delta value, that is our pi by 3. And we can easily see that pi and pi goes away, and this comes as t will be equal to, this will be lambda upon 1.8. Lambda is given to us, so we substituted, we get 5.4 10 to the minus 7 divided by 1.8. So this will be our close to 3 into 10 to the minus 7, or we can write this as 300 nanometers. So this is our thickness, and we can just make a, you can say, estimation of the, sorry, this was t thickness. 1 second. Yeah, we were told that the 5th maxima now appears below and 6th minima appears above. So we are given that our 5th maxima, that is our n is equal to 5, appears below and the 6th minima appears above. 6th minima appears above, and this both is with respect to point P. That is our point P. So we can use the formula, which is our mu2 minus mu1 multiplied by t is equal to m plus minus 1.6 multiplied by lambda. And for m is equal to 5, we can just substitute the values. We will get this as 0.3t, and this is about 5 plus 1 by 6, and lambda we already know is our 5.4 into 10 to the power minus 7. So this gives us a t will be close to 9.3 micrometers. So we come to the next question. I think this completes. Let me check. Yes. So we come to the next question. It was also asked in the year 1997, and it states that in Young's experiment, the source is red light of wavelength 7 into 10 to the power minus 7 meters. When a thin glass plate of refractive index 1.5 at this wavelength is put in the path of one of the interfering beams, the central bright fringe shift by 10 to the power minus 3 meter to the position previously occupied by the fifth bright fringe. Find the thickness of the plate. When the source is now changed to green light of wavelength 5 into 10 to the power minus 7 meter, the central fringe shifts to a position initially occupied by the sixth bright fringe due to red light. Find the refractive index of the glass for green light. Also estimate the change in the fringe width due to the change in the wavelength. This is almost the same question as the previous one, but with minor difference that here we are having two sources of light, red as well as green, and the shift here is given in terms of 10 to the power minus 3 meters. So there are lots of data in this question. So let us first of all write what are the various things that are given to us. Okay. So first is our wavelength of our red light. That is, wavelength for our red is given as 7 into 10 to the power 7 meters. And we have given the refractive index for red light, that is our NR is equal to 1.5, and the shift in central fringe for red light is also given. So we can say that delta Y for red is also given as 10 to the power minus 3 meters. And the order of shifted fringe for red light is also given. So we can say our MR is also given, that is our 5. And we are given the wavelength for green light, lambda G is also given, that is our 5 into 10 to the power minus 7. And the order of shift for green light is also given, that our M of G is also given as 6. And in this question, we have mainly used two formulas. One is shift in the fringe pattern, that is given as mu minus 1 multiplied by T, capital D, and divided by small d. Another one will be about the formula, that is beta is equal to lambda D upon D. So in this case, we are supposed to find out the thickness, which is our first part. So let us start with the thickness of the plate. So for thickness of plate, we are going to consider the shift in the fringe width pattern. Shift in fringe width pattern, that is given as delta Y, and this delta Y, and this is for red. So delta Y will be equal to refractive index of red minus 1 multiplied by thickness D and small d. And it is given that the shift is equal to the position of the fifth bright fringe. Okay, that is also given in the question. So we are given the shift is equal to the position of fifth bright fringe, of fifth bright fringe. So we can write our delta y will be equal to our MR, that is our order of shifted fringe, multiply by its beta, that is our beta R. And we can write this as delta y will be equal to MR. Beta we already know is our lambda d upon small d, and here is a length of a wavelength for the red. Okay. Now we can equate these two equations, and delta y for the red is given. Okay, so this is for delta y for the red, and this is also delta y for the red. Let us call the equation number 1 and this as equation number 2. Equating equation 1 and 2. From equation 1 and 2, we can write refractive index of red minus 1 multiplied by thickness capital D upon small d is equal to MR, and this we have wavelength for the red capital D upon small d. This D and D and D and D cancel out, and we can just solve it for T, and this gives us that our T will be equal to, we have MR lambda R, and this is our refractive index for red minus 1. Now we can just substitute the values. We get our T, MR is given as 5, wavelength is our 7 into 10 to the power minus 7, refractive index is 1.5 minus 1, and this gives us that value of T will be close to 7 into 10 to the power minus 6 meters. Now we are going to discuss the same thing with respect to now the green pattern, green wavelength. So you can say shift in the fringe pattern for green light. And we can say it for delta y prime, and that will be equal to refractive index for green minus 1, and we have thickness that will be same capital D upon small d. Okay. And once again we are going to write the shift position is equal to the sixth bright fringe for the red light, for the red light, green light, yeah, red light. Okay. And we say the shift is equal to the position of the sixth bright fringe for red light. So once again we can say that, and this for green, we can say that we have delta y prime for green will be equal to M for green, and this fringe width will be for red. We substitute for red, we get this as mg, wavelength for red capital D upon small d. Once again let us put this is equation number 3, this is equation number 4. From equation 3 and 4, from equation 3 and 4, we can write that our refractive index of green minus 1 d capital D upon small d is equal to m for G, and here we have wavelength for red d upon small d. This d and d cancels out, and we can solve it for refractive index for green because wavelength we already know, mg we already know. So we can say refractive index of green will be equal to, this will be our mg lambda r divided by t, and this comes plus 1. We substitute the values, we get refractive index for green will be equal to 6 into 7 into 10 to the power minus 7 and 7 into 10 to the power minus 6, and this comes plus 1. So this gives us the refractive index for green will be coming close to 1.6. Now we come to the fringe width part. So we already know that formula for fringe width for red, that is our beta red, will be equal to wavelength for red capital D and small d, and for green, that is our beta G, will be equal to lambda G capital D and small d. And we can find out the change in the fringe width. Change in fringe width, that is our delta beta, will be equal to beta for red minus beta for green. So D and capital D will be common part, so we will get this as lambda r minus lambda G, and this comes capital D upon small d. But we also know that our delta y is equal to, we have this as mr and delta r d upon small d. So from here we can write our capital D upon small d will be equal to delta y, and this is our mr and this is our delta r. So therefore we can write that our delta beta will be equal to lambda r minus lambda G, and this comes as delta y, and we have this as mr and our delta r. Now we can just easily substitute all the values, and keep in mind this delta y is for red, and here also it is red. So wavelength are given to us, so we can write here 7 minus 5 into 10 to the power minus 7, and delta y in red is our 10 to the power minus 3. This comes divided by 5 into delta red is our 7 into 10 to the power minus 7. So this gives us that our delta beta will be approximately equal to 5.7 into 10 to the power minus 5 meters. So this was, I think, all the things. Yeah, change in fringe width due to change in wavelength. So we come to the next question. And in the next question, it was also asked in the year 1997, and it states that a thin equiconvex lens of class of refractive index mu 3/2 and focal length 0.3 meter is in air, is sealed into an opening at one end of tank filled with water mu 4/3. On the opposite side of the lens, a mirror is placed inside the tank on the tank wall perpendicular to the lens axis as shown in the figure. The separation between the lens and the mirror is 0.8 meter. A small object is placed outside the tank in front of the lens. Find the position relative to the lens of the image and object found by the system. Okay. So in this case, we are given that we have a, you can say, a equiconvex lens, and that is just kept inside the, at the mouth of the, you can say, a tank which is consisting of water, and then at the end of the water there is a mirror, okay, inside the tank was perpendicular to the axis. Okay. So this is our equiconvex lens, and the width of this water tank is given as 0.8 meter. So we are supposed to find out that a small object is placed somewhere here, and we have to find out the position of the image of the object formed by the system. So this system consists of equiconvex lens, you can say water, which will be acting as a different refractive index, and then there will be a mirror. So it will be a combination of all these three parts. So first of all, we can say if we have a lens and if R is the, you can say, we can find out the focal length of this equiconvex lens. Okay. So we can use the standard formula, and that standard formula states that 3/2 and 4/3. Okay, yeah. So at the one side of this equiconvex lens we have air, and to the other side we have a water, and we are given that the thin equiconvex lens of the lens is having a refractive index of 3/2 and the water is having a refractive index of 4/3. So therefore we can just write the formula that the focal length F we will get this as 1 upon F is equal to refractive index minus 1, and this comes as 1 upon R1 minus 1 upon R2, and this is equiconvex. So therefore our R1 will be equal to R2, and let us suppose that is equal to R. So we simply substitute the values. We will get mu will be the ratio of 3/2 and as well as the 4/3. Okay. So this will be giving us 3/2 minus 1, and we get this as 1 upon R, and this will be a minus of minus 1 upon R. So we get this as 1 upon F will be equal to, this will be coming as 1/2, and this will be over 2/R, and 2 goes with 2, and this gives us that the focal length is equal to over R, which is nothing but the radius of curvature. Okay. And the focal length is given as 0.3, so this will be equal to 0.3. Now if we say that the refractive index of the lens material is suppose mu2, so say that refractive index of lens is our mu2, and 1 second. Yeah, we have 2 refractive indexes. Okay, so there will be total 3 medium will be there: air, lens itself, as well as water. So we can write that the formula will be our mu3 by V minus mu1 by U is equal to, this will be mu2 minus mu1 divided by R1 plus mu3 minus mu2, and this will be divided by R2. And we already know that both R1 and R2 are equal. So R1 is equal to R2, that is our 0.3, and mu1 is our mu of air, and that is equal to 1. And mu2 is our refractive index of glass that is given to us, and this is our 3 by 2, and we have mu3, that is our refractive index of water, that is also given to us, that is given as 4 by 3. And we are also given that so we can just substitute the values, yeah, more or less is there. So we can write that 4 by 3 upon V minus, and this comes as 0.8. Yeah, the separation between the lens and mirror is 0.8, and a small object is placed in front of the lens. Okay, so we can write this will be our 0.9 is equal to, this will be over 3 by 2 minus 1 divided by 0.3 minus, and here we have 4 by 3 minus 3 by 2, and also it equal to minus of 0.3. And from here we can easily find out our V, that our V will be equal to 1.2 meters. So we can say that this is, let us suppose, image I1, okay, at a distance of 1.2 meter from lens, and it will be to the right. So we can just draw the figure for this particular thing, and we have our, this is our lens, and we have the principal axis, and this is our tank, and the object is somewhere here. This is our object. Therefore the ray of light will be coming something like this, and it will be bent. Let me make it solid. So it will be bent in this direction, and similarly will be for other part also. And it will be also bent in this direction. And if there would have been no, we can see mirror, which was here, it would have converged somewhere here, and this is our I1. Okay. And we just found out that this distance is our 0.1, one second, it is 0.1 meter, or this will be 1.2 meters, this distance of I1. Okay. Now this I1 is going to act as a virtual source for the plane mirror. Okay. So we can say this I1 will act as a virtual object for plane mirror. And it is going to form a real image and forms a real image at, you can say it is going to form a real image, and so we can just draw that also. So it will be reflecting this way, and this will be the position of the real image. And let us suppose that is of I2, real image I2. And now this real image will further act as a, you can say, object for the lens. This real image I2 acts as an object for the lens. So once again, we are going to use same formula, but now for the different parameters. Okay. So you can say now we can use that our mu2 prime divided by v minus mu1 prime divided by u will be equal to mu2 prime minus mu1 prime divided by r1 plus mu3 prime mu2 prime and divided by r2. And now everything is going to shift, so we can say our mu1 prime will be refractive index of water in this case now, and water is having a refractive index of 4/3, and we have this as mu3 prime, that will be our glass, and glass is having a refractive index of 3/2, and our mu2 prime will be our air, which is having a refractive index of 1, and we have r1 which will be equal to now minus of 0.3, and we have r2 which will be now plus of 0.3, and we have our u. Let me denote this also, double prime and double prime. Double prime will be equal to 0.4 and v double prime we have to find out. We simply substitute the values, we get 1 upon v double prime, and this is minus upon is our 0.4 is equal to, and this comes as mu 2 prime. Mu 2 prime is our 1 minus mu 1 prime. Mu 1 prime is 4 by 3 divided by, we have r1 is minus 0.3. This is our mu 3 prime. Mu 3 prime is our 3 by 2 minus mu 2 prime is our 1, and this comes at divided by plus 0.3. So this gives us that our v double prime will be equal to 0.9 meters. So it means we are going to have a formation of, so we can say this is the image I3 formed to the right at a distance of 0.9 meters from the lens, and is virtual. Okay. So it means the final position of the image, you can say the final position of image is our I3, final image of position of image is I3 will be 0.9 meters to the right of lens. So we can also draw this I3, okay, and this will be also our virtual image, okay, and this will be something like this. So this will be our I3, and distance from the lens will be 0.9 meters. So we can just complete this part. So it will be bending in this direction, and this will be also in this direction, okay. And this can be extended in the backward direction, this also, okay. So this completes this particular question. We come to the next part. It was asked in the year 1998, and it states that a spherical surface of radius of curvature r separates air refractive index of 1 from glass refractive index of 1.5. The radius of curvature is in the glass. A point object P placed in the air is found to have a real image Q in the glass. The line PQ cuts the surface at a point O such that PO is equal to OQ. The distance PO is equal to. So we can first of all draw an approximate figure. So we are given that there is a lens something like this, and this is the principal axis. We have a point O, and we have point object at P, and image is formed at Q, and it says that this PO is equal to PQ, and we can just draw the ray diagram. It will be coming like this. So refractive index, let us suppose this is air, is given as 1, and we have glass with refractive index 1.5, and we are given that our PO is equal to our OQ. Let us suppose that is equal to X, and so distance of the object, that is our PO, will be equal to minus of X. So we can say our U is equal to minus of PO, which is our minus of X, and also our V, which is our OQ, will be equal, plus OQ rather, will be equal to plus of X. Now we can use straightforward formula, that is our mu2 minus mu1, mu2 upon V minus mu1 upon U is equal to mu2 minus mu1 upon R. So everything is given to us. We simply substitute the value. Mu2 is our 1.5 upon, we have plus X, minus, this is 1 upon minus of X is equal to 1.5 minus 1 divided by R. And this gives us that we can write this as 1.5 divided by X plus 1 by X is equal to 0.5 divided by R, and this tells us that our X will be equal to 5 times R. So option number A is correct option. Option A is correct. Okay. So we come to the next question. It was also asked the year 1998, and it states that a concave mirror is placed on a horizontal table with its axis directed vertically upwards, and it says that let O be the pole of the mirror and C is the center of curvature. A point object is placed at C. It has a real image also located at C. If the mirror is now filled with water, the image will be. So this is, we can say more or less, we can just make an analysis with the help of figure of the drawing the diagram also. Okay. And we can use that diagram in two conditions. In the first condition, we are given that we have a concave mirror which is placed on a table. So this is a concave mirror, and we have an object which is placed on the principal axis. So this is our object, that is our C. So obviously the ray of light will be traveling in this direction, and same on the other side also. But for final condition, it is said that it is being filled with the water. Okay, so now it is filled with water. So object is still at C, and now the incoming and outgoing or reflected or incident will be traveling in a different way. This is our incident. It will be bending towards the normal, something like this, and then it will be reflected. It will be bending away from the normal, and somewhere here it is going to meet. And same process will be from the other side also. Yeah. So this will be our formation of the image. We can also find out the actual position of the, you can say, what will be the distance. Okay. So this is our initial condition, and this is our final. And in the final condition especially, in the final condition, the total system it consists of water lens effect twice and concave mirror effect once. So we can say to total system will be having a water lens effect that will be twice and plus concave mirror effect. This is concave mirror. Concave mirror effect. So it means we can write the formula that the effective focal length of the system, focal length for total system, and that is suppose capital F. So we can write 1 upon capital F will be equal to twice multiply by 1 upon focal length of water lens plus 1 upon focal length of concave mirror. And it's basically you can say plano-convex lens of radius r. Okay. So therefore we can write that our 1 upon f for water lens will be equal to mu minus 1, and this will be our 1 upon r. And for mirror you can write 1 upon concave mirror will be equal to 2 upon r. So we just put the values, we get 1 upon f is equal to twice mu minus 1 upon r plus 2 upon r. And we can just solve it. We can take 1 upon r is common, and this will be coming as 2 mu minus 2, and this will be plus 2 upon r. This minus 2 plus 2 cancels out, so this comes as 2 mu upon r, and we can say that our focal length will be equal to r upon 2 mu for the entire complete system. Okay. So our mu is our greater than 1, so therefore we can say that new effective focal length is shorter than the original one, than the original So it means if we have the pole is at O. So this is O, and there will be image that will be between pole C and 0, okay, and it will be a real one. So option D is correct. So next question. It was also asked in the year 1998, and it states that a ray of light traveling in a transparent medium fall on a surface separating the medium from air at an angle of incident 45 degree. The ray undergoes total internal reflection. If n is the refractive index of the medium with respect to air, select the possible values of n from the following. Okay, so we have to find out the possible values or possible value of the value of n. And here it is for total internal reflection. So we can say that total internal reflection occurs. First is that light travels from denser medium to rarer medium. From denser medium to rarer medium. And secondly, the angle of incidence should be greater than the critical angle. The angle of incidence, that is of I, should be greater than critical angle, which is our suppose theta c. And critical angle, the formula we already know, that our sine of theta c is equal to refractive index for air and refractive index which is given for the material. So this will be 1 upon n. And we are given that the angle of incident is 45 degree. Okay. So we are given that angle of incidence, that is of I, is our 45. So we can say that the total internal reflection occurs when our I is greater than theta c, or we can say our theta c is less than 45 degree. And from here we can just write it that sine of theta c is ever less than sine of 45, and sine of 45 is 1 upon square root of 2, which is close to 0.707. So this sine of theta c is 1 upon refractive index is less than 0.707, and which gives that the refractive index should be greater than 1 upon 0.707, which is approximately 1.414. So any option which is giving us a result that refractive index is greater than 414 is our valid option. So we can check the given condition. So anything greater than 1.4, we have only 2, that is C as well as D. We can say option C and D are correct. Option C and D are correct. We come to the next question, and it was also asked in the year 1998, and it states that the prism of refractive index n1 and another prism of refractive index n2 are stuck together with a gap as shown in the figure. The angles of prism are all shown. N1 and n2 depends upon lambda, the wavelength of light according to. So we have two equations separately for n1 as well as n2. Based on this, we have two questions. First, calculate the wavelength lambda naught for which rays incident at any angle on the interface BC pass through without bending at any surface. And B part, for a wavelength of lambda naught, find the angle of incident I on the face AC such that deviation produced by combination of prism is minimum. So we have two lenses, refractive index n1 and n2, and there are various angles associated with the 60, 40, 20 and 70. Okay, and incident ray is first incident is at AC, and in this case we have to find out that first part for which with respect to interface BC. Okay, so we have to find out with respect to this interface our BC, and in this case we are going to use two things. One is our Snell's law, and second one is that there should be no you can say without bending. Without bending means the refractive index of both n1 and n2 should be equal. That is the only condition under which there will be no bending. Okay. So we can say no bending means our n1 is equal to our n2, and both equations are given to us independently, so we can just substitute them and we can get this as 1.2 plus 10.8 into 10 to the power 4 divided by lambda square and equal to 1.5 plus 1.8 10 to the power 4, and this is our lambda square. So we can just quite easily solve it now, and combine the lambda terms to one side. Yeah, so we get this as 1 upon lambda square. We have this as 10.8 minus 1.8 10 to the power 4 is equal to 1.45 minus 1.2, and from here we can write that our lambda square will be equal to 36 into 10 to the power 4, which gives us the lambda will be our 6 into 10 to the power 2, or we can say 600, and that will be in meters. And then we have to find out, sorry, not meters, 1 second, nanometer. Wavelength is given as nanometer. Okay. Then we have to find out that there should be a minimum deviation. Okay. So we have part B, and now the wavelength is our lambda naught. Okay. That was asked. So we can say for lambda naught is equal to 600 nanometer, we can complete the figure. Okay, let's draw the figure first. So we are given a prism which is like this, and so if we complete it, this will be the completion of the triangle, both. And let us suppose this is our A, this is our B, C and D, and let us call this as point E. We are given this as 60 degree and 60, 40 and 20. So this is 60, this is about 40 and this is about 20. So this entire angle will be over 60. So this gives us that this angle E will be also over 60, which is basically an equilateral triangle. Okay. And this angle is given to us as 70. So we have to find out the minimum deviation. So you can say that for lambda naught, that is our 600 nanometer, at minimum deviation, the ray let me connect the charger. So you can say the ray inside the prism will be parallel to the base of the prism, will be parallel to BC. So we can say if this is our incident normal, and we are going to have the refracted ray will be going through like this, a parallel. So this will be our I and this will be our R. And because of the parallel, this angle will be of 60, and this gives us that our R will be our 30. So therefore we can say that angle R will be equal to 30 degree. Now we can easily use our Snell's law, which gives us that our it is coming from air, so we can say N1 sine of I will be equal to N2 sine of R. And okay, we have N1 for this one. Let me write this N, and this is our N1. So N is for air, so let me write for this as air, that is 1, and this gives us that sine of I will be equal to N, and this is our sine of 30, which comes as N by 2. And we can find out value of N for 600 nanometer, because we know the relationship between N and the wavelength. So we can say our N will be equal to 1.20 plus 10.8 into 10 to the power 4 divided by 600 and whole square. So this comes as 1.5. Therefore we can say that our sine of I will be equal to 1.50 divided by 2. So this gives our I will be equal to sine inverse 3 by 2. And I think this was only thing that was asked. Yeah, so these were the two things which were asked in it. And let's come to the next question. It was asked in the year 1998, and it states that a coherent parallel beam of microwave of wavelength lambda is equal to 0.5 millimeter falls on the Young's double slit apparatus. The separation between the slits is 1 millimeter. The intensity of the microwave is measured on screen placed parallel to the plane of slit at a distance of 1 meter from it as shown in the figure. So we have two questions based on this description, and it states that if the incident beam forms normally on the double slit apparatus, find the y coordinate of all the interferences minima on the screen. And in the B part, if the incident beam makes an angle of 30 degree with the x-axis, as shown in dotted arrow shown in the figure, find the y coordinates of first minima on either side of central maxima. Okay, so we have this figure, we have a screen. The distance between these are two slits. Distance between the screen and slit is 1 meter, and distance among the slits is 1 millimeter. And here the cases are two. In the first case, the rays are just normal to the slits, and in the second case it is at an angle of 30 degree. And we have this as a, you can say, screen. Okay, so let us draw a figure for the first part in which states that it should be parallel. So we have two slits, and let us call this as slit S1, and this is slit S2, and it is parallel, so it will be coming like this, and this is our central part, and we suppose they meet at a point P, and we are supposed to find out this coordinate y. And obviously there will be some phase difference, path difference because of this, and from the center also we can just draw it, and for this will be our path difference. And if theta is the angle, so we can say this distance or difference will be d sine of theta. And we can also write it as that the position of point on screen, we can write this as that y will be equal to d tangent of theta, and d is given to us because this is our capital D, this is our 1, so this comes as tangent of theta. So therefore for first minima, we can write value of n is equal to 1, and this gives us that our sine of theta 1 will be equal to 1 by 4, and lambda, okay, and we can write that our tangent of theta 1 will be equal to 1 upon square root of 15. For second minima, value of n will be equal to 2, and this gives us sine of theta 2 will be equal to 3 by 4, giving us tangent of theta 2 will be equal to 3 by square root of 7. And the position of the minima, both the minimas, so position of minima, that is our y1, will be equal to tangent of theta 1, which is 1 upon square root of 15. This comes as close to 0.258 meters. And similarly we can write for y2 also. Y2 will be giving us tangent of theta 2, that is our 3 upon square root of 7, and this comes as 1.13 meters. Okay, and they will be symmetric about the, you can say, the central one. Okay, So from here we are going to get plus minus 0.258, and this will be also plus minus 1.13 meters because of the symmetricity. And we also know that condition for minima at y-axis condition of minima at y-axis, we have our d sine of theta is equal to 2n minus 1, and this comes as lambda by 2. So this gives us that our sine of theta should be equal to 2n minus 1 times lambda, and this comes as 2d. So we can just substitute the values which we know. So we get our sine of theta will be equal to 2n minus 1, lambda we know that is our 0.5, 2d also we know that is our 1. So this comes as 2n minus 1 and divided by 4. And we can also say that our sine of theta is our less than equal to 1. So this gives us that 2n minus 1 divided by 4 should be less than equal to 1. Or from here we can write our n should be less than equal to 2.5. Okay. Next we can find out for the part B now, which is at the angle of you can say 30 degree. So we have part B, and in this case there will be path difference before and after the slits. So we can just draw an approximate figure for that also. And there is an angle of 30 degree. Suppose this is our slit S1 and this is our slit S2, and they will be somewhat traveling in this direction. So this angle will be about theta. So we are going to have a difference, path difference rather, on the both sides, and this angle is, let us suppose, our phi. So we can, this angle will be about theta. So we get here a d sine of theta, and here will be our d sine of phi. And we are once again going to find out this. So we can write the equation that the path difference d sine of theta minus d sine of phi will be equal to plus minus lambda by 2. So we can say that our d is given to us 1. So therefore we can write this as sine of theta will be equal to sine of phi plus minus lambda by 2. And phi is given to us at 30 degree. So this is about 30. So we can write that sine of theta is equal to, we have here sine of 30 plus minus, we substitute the value, this comes as 0.5 and divided by 2. So this comes as plus minus, so this will be either 3 by 4 or this will be 1 by 4. From here we can write that our tangent of theta will be either equal to 3 by 7 and this will be equal to 1 upon 15. And we can say, because in the second case we are supposed to find out only the position of first minima on the either side of central maxima. So you can see that position of first minima on either side of central maxima we get y is equal to capital D tangent of theta, and that is also given as 1. So we can write this as 3 by square root of 7 and 1 by square root of 15 meters. So these were, so this completes the questions, all the questions. So total of there were 10 questions. 4 were from the year 1997 and 6 were from the year 1998. So this completes all these 10 questions. Thank you.